Hello and welcome back to this wireless telemetry antenna lab tutorial. In this tutorial we're going to be covering how to complete an EM thermal coupled simulation. And so what we have here is the coaxial connector that we created in a previous tutorial. We're now going to create a coupled simulation to simulate what happens to this connector in the electromagnetic domain and then take the heating that is produced from those electromagnetic sources and simulate how much heating this coaxial conductor experiences by doing a thermal solver simulation. So to set up this coupled simulation, we're going to come down here, and right now we're in the 3D view. We want to change to the schematic view. So we'll change to the schematic view, and we want to create a new task. We want to create a simulation project. So we come down here to EM thermal coupling, unidirectional, and it'll now prompt us to create the different simulation projects. So we'll come up here to create simulation project. First we're going to create the EM domain. It'll auto define it as EM1. You can name it whatever you like. For the sake of this tutorial, I'm just going to leave it. We want to simulate this in CST Microwave Studio. We're not going to have any project template. The solver we're going to use for this is the transient. In future videos, I'll explain the kind of decision making you can go through to decide whether you want to use a transient domain solver or a frequency domain solver, but for this simulation and for this example, we're going to use a transient solver. And then just leave this alone. And we want to link geometry to the master model, meaning that that model we created in the previous video, we want all of the changes we make to that model to be reflected across both projects. So we'll go ahead and create this. And now it will prompt us to create the thermal project for the thermal simulation. So we'll come back up here to create simulation project. Again, it autofills it as thermal 1. You can rename it for this video. I'm just going to leave it as is. And the only possible studio we can simulate this in is M-Physics Studio. There are a couple of different solvers that we can use, and I'll go over in a future video what the different type of solvers do. For this simulation, we're going to be doing a thermal transient solver. And again, everything's the same, so go ahead and create it. Alright, so now we have our two files, as seen here. It will ask us one last thing. It'll ask us the minimum and maximum frequency, so 0 to 15 gigahertz. The frequency for loss computation, in other words, the frequency at which we're going to calculate the electromagnetic losses that result in that thermal heating, is going to be 7.5 gigahertz. And again, you can go back to the help contents and refer to sort of the verbal explanation of this walkthrough. Now, the scaling factor for losses. In CST, it will, in a transient solver, it will provide a Gaussian pulse. And this allows us to scale that Gaussian pulse to what power input we're using. So in other words, a scaling factor for losses of 1 just assumes a 1 watt input source. If we wanted something larger, say 20 watt or 50 watt, we would scale the losses accordingly. This can get a little bit tricky, and again, I'll explain using the scaling factor appropriately to effectively model what your signal generator is doing. And again, this goes into why you might use the transient solver or the frequency domain solver, depending on what kind of excitation signal and what kind of source is generating that excitation signal. We're just going to leave this at 1 for now, though. All right, so in essence, we've finished. We've created our coupled simulation. We have our two different projects. However, there is some setup that we need to do in each of these projects in order for the simulation to run correctly. All right, so the first thing we're going to do is go to the EM project. This is the microwave studio, the electromagnetic side of this project, and we need to check a couple things. So the first thing we want to check is what field monitors have been defined. So we can see some field monitors have already been defined for us. It has automatically defined the E field monitor, H field, so electric field and magnetic field, and then this loss monitor. And so these are the monitors that are going to be used in order to calculate what kind of thermal losses are produced, and that will produce, that calculation will produce numbers that then are transferred over into this thermal simulation, and we'll see that in action in a moment. So we verified that the correct field monitors are defined. The other things that we want to verify are the things that we would do for any simulation, and the things that we already did in that 2.4 gigahertz introduction simulation. And so that is, we want to check the boundary conditions. So right now, it is a conductive box on all of these sides. I'm going to go over to the CST example to see what boundary conditions they used in their simulation. So if we open that up, so in their simulation, they have actually done magnetic boundary conditions, and they have taken advantage of symmetry planes. So this structure is symmetric on both the YZ plane and the XZ plane, and this allows the solver to do essentially a fourth as much work, because it's not simulating this quadrant, or this quadrant, because it can assume what those results are. So we are going to match this in our version of this simulation. So we will go to boundaries. We can hit this apply in all directions, and we're doing magnetic. Now, symmetry planes, magnetic symmetry, and look for my future video explaining what these different boundary conditions mean and how you use them. But for now, we're just going to follow this example. All right, so we've correctly defined the boundaries. We now have to define the background. As a default, it assumes the material background is PEC. Usually you want to change this to be air. I guess before I do this, I'm going to make sure that they did that also. Oops. Background, not boundaries. Yes. So see, in their simulation, they also have changed the background to not be PEC. I don't want to get too much into why you do that. For now, my only explanation is going to be that you cannot have the background type be PEC if you want those field monitors to work the way you expect. So if you want an accurate representation of the electric field, the magnetic field, and the surface losses, you cannot have your background to be PEC. And I'll explain more about that in a future video. All right. So let us do the same. We did. The other thing that they did in their simulation is they want to set a bit of surrounding space. So in their simulation, they set these distances. So we will follow suit for this simulation. Oops. Gotta be careful switching between mine and theirs. Background. Alright. So we're just going to do 5 for the X. And that is providing sort of additional space here. So we're providing a little bit of additional space where the simulation is defined. We don't provide any additional space in the Z direction because there's no reason to. We just have this excitation right here and this excitation right here, and we're not wanting to represent anything in addition to that. So this goes to sort of thinking about what this is like in the real world situation. So in the real world situation, this structure is going to be connected and this structure is going to be connected, and we model that using port waveguide excitations. However, in the real world, there's going to be air, around this connector. And so this background allows us to appropriately model that. So that's everything on the electromagnetic side. We're now going to save this project and then move over to do similar setup on the thermal side. Before we switch over to the thermal project, I forgot one last crucial thing that we need to do on the EM project, which is we need to define our excitation sources. So currently we have our default excitation, but we have no ports to deliver that excitation. So we'll go to modeling. We want to pick faces. Let me come down here. Pick points, edges, or faces. We're going to pick this face. And then we will come to simulation, waveguide port, and see it's using our pick. Now, this came up in the patch antenna video, and I just want to reiterate it again. You need to make sure your port excitation is in the correct direction. So as we see down here, we've got this vector port showing it going in the positive direction. If we put it going in the negative direction, it would be coming out. Alright, so we have our first port, so we'll click OK. And now we need to define the second port, because remember, this is acting as a transmission line, not an antenna. So we'll rotate around. Remember, that's just holding the control button down and then rotating. And we'll do the same thing. We will pick this face here. And then create a waveguide port based on that pick. Okay. So again, we need to make sure that the propagation direction is correct, so it's going in the positive direction. And so now we have our ports defined. Because we have our ports now defined, let's go back to this view. Now we can set up the simulation properly. So they take their accuracy down a little bit to make the simulation run faster. So just know that the simulation will be less accurate. In addition, they don't perform adaptive mesh refinement, which means, again, the accuracy of this simulation is going to suffer. But where we're just demonstrating this as an exercise in how to do a coupled simulation, we don't really care. So now we have to define this source type. So the excitation is coming from a specific port. It's not coming from both. So what this means is, this would be like if we hooked our coaxial connector up to a generator on one side and maybe an antenna on the other side. You don't have an excitation coming from both sides of the port, and in this case we're going to simulate it as port 1. So we apply that and we close. Now we can move on to the thermal simulation. Alright, so we are now in the thermal project for this coaxial connector. So notice that these menus look very much the same. However, the simulation sources are going to be very specific to a thermal simulation. So essentially we have different options here, but the interface is still very much the same. So we're going to do the same things that we did in the EM simulation. That is, we're going to define the boundaries. And it has already assumed some boundaries for us. Looking at the other boundary conditions, they set them like this. And then we will take advantage of these symmetry planes again. So now we've set our boundary conditions. And now we need to set our background conditions. So again, the material type cannot be PEC. We're going to take it a step further in the thermal simulation. We're going to copy properties from a material. Specifically, we're going to assume that the background is air with these properties. And then we will do the same additional background space that we did in the EM simulation. So that's 5 millimeters on each side. but no additional space in the z direction, because again, that's our excitation signal, or where it's connected to a signal in, say, an antenna. So it doesn't make sense to have additional background space there. Then the last thing we do is go to our setup solver. And we need to set a simulation duration. So let's come out of this and see how they set their simulation duration. They did it different. All right, so it's come to my attention that in the CST example, they used a steady state thermal solver, and I mistakenly told you to do a transient solver. And so we need to correct that. So the way that we do that is we come back to the master project. We'll click on the simulation and we'll click on properties. So we'll change it from thermal transient to thermal steady state and click OK. So now when we go back to this menu, we should see that the setup solver has changed. My apologies for that. And so now, but the work that we've done on the background and boundaries is still there, so we don't need to do anything there. We just need to finish setting up the solver. And we're going to set the ambient temperature to Celsius, and we're just going to have it be 20 Celsius, which is room temperature. And now we have our simulation results, or our coupled simulation set up. Now, you should be ready to go. However, there is a hang-up, which I alluded to in my previous video, and that is that they have failed to provide us with any information about the density or the specific heat. And so I argued that that would limit the solvers that we would be able to use, and in fact it might make it so the simulation doesn't work at all. So if we come over here to intersection check and we do a thermal material check, it will warn us. It says you can't complete this simulation without heat capacity and density settings for each conductive material. The following materials have a thermal conductivity setting, but a heat capacity and or density setting was not defined. And these are the materials we defined in my previous video where I showed you how to model this connector. Unfortunately, this is not an oversight on my part. In their project as well, so their master project, the one that CST provides, they also run into this issue. And so what this means is that we're going to have to get a little creative with our simulating. So join me for the next video where I'll go over how to fix this problem and then show you how to actually run the coupled EM thermal simulation.